everyone. Today we're going to be going over scatter plots and line of best fit. Our goal today is to be able to collect data and use scatter plots to analyze patterns and describe linear relationships between two variables. A scatter plot is a graph that shows the relationship between two data sets, and they're generally just a series of points on a graph. But those points on a graph are still valuable because they can show us some relationships between our variables. So let's take a look at our first graph. The scatter plot shows the amounts of time, x, and hours that 8 students spend on homework each week, and their grade point averages, y. It is always good to familiarize yourself with both the x and y axis to understand what they're looking at. Our x-axis points out the weekly hours students spent studying, and our y-axis looks at the grade point average, or GPA, of those students. So we take a look at our first question. What is the grade point average of the student who spends 6 hours a week on homework? If we take a look here, we are going to look for the number of hours a week because it's asking us 6 hours a week. So we're going to look at our x-axis and see that we cannot find 6 automatically. So we double check our scale and we can see that it is going up by 2s. So we can fill in those numbers and help ourselves out, and we can find 6 quickly on the x-axis. Once we find 6, we're going to look up and find the point. And from there, we'll look to the left of the graph and see that this person earned a 2.0 GPA. It is always good to label things, otherwise you may not understand what is going on with that number. Now let's look at part B. B is asking us how many hours a week does a student who has a 2.75 grade point average on homework. So that lets us know we need to look at our y-axis because it's talking about grade point average. So if we look here, we can see that it looks like it's going up by 1s, but there's a space in between. So that lets us know if we cut 1 in half, we're actually going up by 0.5 each and every time. So I'm going to fill this in just to help myself so I can read the graph a little easier. And now I'm going to be looking for 2.75, which unfortunately is not on this graph. So we can look between which two numbers would it be between. In our case, it would be between 3 and 2.5. And it's actually in the very middle. So if I look to the right, I can find the point that is 2.75 and look down and see that that person spent 12 hours studying. And then in part C, what tends to happen to the grade point average as the number of hours spent on homework increases? If we look at the scatter plot, we can kind of see that it looks like it's going up. And if it was a line, we would say it has a positive slope, which lets us know that the GPA, the grade point average, will increase as the number of hours of spent on homework increases. So let's build more onto like that, what's going on with the graph. Let's look at what it is called, our correlation. A correlation is the relationship between data sets, and it generally, you can interpret it similar to slope, except for the fact that it is a series of data points. Our scatter plot, it does not form a line. It just has a bunch of points that looks like a line. And that's how we can determine our correlation. A positive correlation looks like it has a positive slope. So as x increases, y also increases. A negative correlation looks like a negative slope, which gives us the idea that as x increases, y will decrease. And no correlation just looks like a bunch of points on a graph that is just randomly put to where. It has neither a positive nor negative correlation, and it doesn't even show a pattern. So we call this no correlation. And let's use that on our next bit of examples. So we're going to take a look at our first graph, and we're asked to see if the data shows a positive, negative, or no correlation. In our graph, it is talking about stopping distance. Our x-axis talks about the speed in which we are going. I'm going to probably predict we're in a car or some other vehicle. And the distance that it takes to stop. So we're looking at the relationship between the speed and the distance. And if we look at the graph, as speed increases, our graph also on the y-axis increases. This lets us know we have a positive correlation. And if we look at our next example, we're going to take a look to see if there's any correlation between birth month, the month you're born in, and how many hours of sleep you get each night. So if we look at our x-axis, it is labeled with all the months in a year. And on our y-axis, it talks about how much sleep on average these people born in this month gets. And if we look at our information, it makes no sense. Months repeat, different people are in different amounts. There is no positive looking or negative looking line made out of the points. Therefore, we can see that this is no correlation. Now we're going to be talking about lines of fit. We're going to be able to look at lines of fit more in depth in our next section, but I want to bring it into what is going on. So a line of fit is a line drawn on a scatter plot that is close to most of the data points. Generally, there's going to be the same number of data points above as so below the line that we use for the line of fit. And generally, when we're making a line of fit, we make a scatter plot of the data. And once we make a scatter plot, we see if the data can be modeled by a line. That means we're going to take a look at the correlation. Are we going to see a positive correlation or a negative correlation? If there is no correlation, there is no equation to be made. And then we're going to be able to draw a line that appears to fit the data closely. Again, there should be as many points above said line as below. And from there, we're able to write an equation using 2 points on the line, not from the scatter plot points, but the points on the line. The points do not have to represent actual data pairs, but they must lie on the line of fit. So in our example, we're not going to be necessarily making a scatter plot in this case, but we are actually going to be able, since we have few data points, to be able to see if we can model the equation of a line. So we're going to see if our data shows an increase or a decrease in what's going on. So let's take a look at our example. The table shows the salaries in thousands of dollars of 5 architects and the number X years of experience. We're going to write an equation that models the salaries as a function of the number of years of experience. Then we are going to interpret the slope and the y-intercept of the line of fit. So the first thing we need to do is generally we'd be making a scatter plot. In our case, we're just going to take a look at the numbers because there's not so much. So as we look at our x-axis, or x going on, we see that the numbers increase by 1. And again, that represents the number of years the architects have worked. And in our y variable, we see the salaries of these architects, and we can see that it goes up for each year an architect has worked. It does not go up at a constant rate. They are different. Therefore, it lets us know this is not going to be a beautiful linear equation, but this is where we would need a line of fit. And in our case, we're going to be able to pull from 2 data points today, just to kind of show that it may not work for everything. And in our next section, our line of fit is going to be more thoroughly explained. So we're going to pick 2 data sets. And again, we understand by doing this that it's not going to be perfect. So I'm going to pick 460 and 255. And I'm going to go ahead and write my ordered pairs. And since we can see there's a positive relationship between the number of years worked and salary, we're going to be able to predict it has a positive correlation. Therefore, it has a positive slope. So, we're going to find the slope with our chosen data points. So we're going to find that, M equals 60 minus 55 over 4 minus 2, which gives us 5 over 2, which is, if we were to put it as a decimal, would give us 2.5. And when we are interpreting, it is totally okay to take your improper fraction and convert it to a decimal to be able to understand that fraction better. And we will need that here in a moment. But now we need to find our y-intercept. We can use point slope form. We just have to pick one ordered pair since we already have our slope. So I'm going to pick the ordered pair 460. And I'm going to use my equation for point slope form. So I'm going to have y minus y1, which is 60, equals our slope, which is 5.5. I like fractions better, times the quantity of x minus x1, which is 4. From here, I want to solve for y. I like to use slope-intercept form because it is able to explain a lot of information in a very brief amount. So our first step is to distribute. So we're going to use the distributive property to simplify this equation. So we're going to have y minus 60 equals 5 over 2x minus 10. But we're not done. We want to get y by itself. So we're going to add 60 to both sides. So when we do that, we will see that we get our equation y equals 5 over 2x plus 50. And for interpretation's sake, I'm going to convert my improper fraction back to that decimal so I can be able to interpret this equation more thoroughly. Our slope in this case is actually telling us about the increase each and every year. So slope is the salary increase in thousands of dollars. Make sure you put in thousands in parentheses to let us know our unit measure. So we're saying that our slope is the salary increase in thousands of the money earned with each year of experience. And then our y-intercept. Remember when you're interpreting the y-intercept, you want to make x be 0 so you can interpret it. In this case, if we made our x variable be 0. It means with no experience as an architect, you're just starting out, fresh from school, from college. You've got the degree. When x is 0, it lets us know that our y-intercept, which is 50, means that starting out, the architect will be earning $50,000 a year. And understand that you can look at that and look at our data and see that that is not the case every year. And that shows you that a line of fit that we will go over in the next section really matters about where you place it. Otherwise, it's not going to be perfect. And it is okay if the equation is not perfect within our scatter plot. Again, because there should be as many data points above as so below. Thank you, and I can't wait to see you to the next section.